Hello, it's Ryan again. All right, we're going to pick up where we left off last time. Last time we were talking about forces and the kinds of forces, Newton's three laws, and now we're going to actually start applying them to solve specific problems. One of the tools that we're going to start with is what's called a free body diagram. A free body diagram is a drawing that used to indicate forces acting on an object or a system. A system is basically a single object or a cluster of objects that we are going to describe the motion of. The object is often represented as a dot, but it could also be represented as a box or whatever the object is that you're looking at. If it's a person, you can draw a person. The forces are going to be drawn roughly proportional to their magnitudes. It's not expected to be exact, although if you know that certain forces are equal, you can indicate them with a congruence marker like we would do in a geometry class. And the coordinate system is very important, though it should not be overlaid directly on the free body diagram. It should be off to one side to indicate which directions are positive and negative. They are up to you. However, there are going to be some general rules that we follow, just like with kinematics. Certain directions make sense to make positive. And why are we doing these? Basically, we're going to do them because these diagrams help us set up our F equals ma equations in the x and y directions to actually solve questions. So I'm going to go through a couple situations and then describe how I would draw a free body diagram. So let's say I have a block on a flat surface and it is being pulled to the right by a force. I'll call it FA for force applied. And I'm asked, and let's say this block is traveling at constant speed. I'm asked to draw the free body diagram of this object. Even if I'm not directly told anything else, first of all, I will actually draw the force going from the center, even though it may actually be, formally speaking, we draw the forces acting at the point of contact. So it would be here for the applied force if it's connected. However, until we get to rotations, it's going to be sufficient to either draw it as a box and everything going from the center, or draw it as a single dot. So I will, if I want to draw represent my system as a single dot, I can also draw it this way. What other forces are acting? Well, presumably this is on a flat surface on the Earth. So we've got a force of gravity that's acting downward. And the thing that's keeping it from falling through the Earth would be the normal force, which would be going upward. And because this object is moving at constant speed to the right, we know there's no acceleration upwards or downwards, and therefore these forces have to be equal. So we may want to indicate that using a little congruence marker. Finally, even though it's not explicitly stated, we know that because it's moving at constant velocity, the acceleration must be zero, therefore the net force must be zero. So if we're not told what that additional force is, we may reasonably infer that it's friction. And so because the box is moving, that will be a friction force, a kinetic friction force. And because we know that the net force is zero, this should be equal to this. Note I'm using two dash marks because while these are equal, they're not necessarily equal to these. Represented as a single dot, it would work this way. And as far as a coordinate system, I'm going to make the direction of motion positive. So that would be positive x, positive y. Although the coordinate system is technically at the location of the center of the box, it's best to draw it offset to avoid confusing the axes with the actual forces. Notice that I did not draw the velocity on here. I don't want to confuse the matter, only forces on the free body diagram. Let's look at another situation. Let's look at a situation in which you have a box that is being pulled up and to the right by a force. And now we're going to not say that this is actually at constant velocity. We just know that it's going to be moving to the right. So, so we don't have to assume friction, and let's assume no friction here. So what's happening here? Well, we still have gravity, that's down. Now our normal force is still perpendicular to the surfaces in contact, so it would be going up. However, it's not necessarily equal to gravity. In fact, because the motion is purely to the right and there's no net force vertically, the normal force is smaller than gravity because gravity is balanced by both the normal force and the vertical component of the applied force. And so because those are no longer equal magnitudes, no congruence marker is required. Okay, so keeping with this example, how would we actually use this to solve for, let's say, the acceleration of this object? Well, typically what we're going to do is we're going to solve for F equals ma in at least the x direction, the direction of motion, and occasionally the y direction. So we would absolutely need to solve for the y direction if we were dealing with friction. So if we were solving this problem and we needed to know, let's say, the friction force, because the kinetic friction force has as part of its formula the normal force, we would solve for the sum of the forces in the y direction first, equal to 0, because the acceleration is in the y direction, and then acceleration in the y direction 0. Use that to solve for the normal force, and then set up our F equals ma equation in the x direction. So we could substitute whatever we got in our normal force for the kinetic friction force. So actually just going to this example, just because it's easier to illustrate, equals mass times acceleration in the y direction. Acceleration in the y direction is 0. So I use my coordinate system to determine which direction is positive, which direction is negative. Normal force is positive, gravity is negative. Substituting for mg for gravity, I get the normal force is equal to mg. Now solving for the x direction. In this specific case, my acceleration is 0. It won't necessarily be 0 in most cases. My applied force is positive. My friction force is negative. And then I could substitute using that the kinetic friction force is equal to the coefficient of kinetic friction times the normal force. And the normal force I got from the y direction equation, and I could substitute that. At this point I could solve for the applied force or the kinetic friction, coefficient of kinetic friction, whatever I'm asked for. Going back to this problem, let's say I'm given this angle theta. So in this case, let's say I'm interested in solving for the acceleration. Well, I don't have to solve the y direction. I will go ahead and do so here just to show you how the normal force is a little bit smaller. But because there's no friction, I actually don't need the y direction for this one. But let's go ahead and do it. Acceleration in the y direction 0 because this block is neither moving up nor down, or accelerating up nor down. So the component of the applied force in the y direction, again we can break these up into triangles. That would be the applied force sine theta, and it's positive because it's going upward, plus the normal force minus the force of gravity is 0. So this means my normal force is equal to the force of gravity, which I'll replace with mg, minus the applied force sine theta. So this is lower than it was in this case because, again, the applied force is pulling upwards a little bit, helping to offset gravity, so normal force is a little bit less. Again, we don't need the y direction for this specific problem, but this is how it would work in a case where you needed to solve for normal force in order to plug in and solve for friction. So what about the x direction? What about actually solving for the acceleration? Sum of the forces equals mass times acceleration in the x direction. We have only one force with a component in the x direction. That would be the applied force. So that would be the adjacent side, so that would be cosine theta. So assuming we're given the applied force, the angle, and the mass, we divide the mass, and we get the acceleration, which will be constant, which means we can use this acceleration with our kinematic equations and solve for other quantities of motion: time, displacement, final velocity. Okay, and that's basically what we're going to be doing. This F equals ma work will be related to kinematics via solving for acceleration and using it to calculate other quantities of motion, or using kinematics to get acceleration and then your F equals ma equation to solve for a specific force or a coefficient of friction. Let's look at a couple other examples. I'm going to stick with the slightly more abstract ones. We can always talk about specific problems, but common problem types would be a block on a ramp. So if I have a block on a ramp, let's say it's sliding down the ramp, but it could also be sliding up a ramp. The coordinate system I will use will be aligned with the ramp. I'm going to draw a positive x down the ramp and positive y perpendicular to the ramp. The reason for using a rotated coordinate system is motion will be along the ramp, so it makes sense to align one of the axes with that. So what are the forces acting on this? Assuming no friction, we have force of gravity, normal force, and that may be it. And so if I have something like this, how would I actually solve for, let's say, the acceleration down the ramp? Well, normal force is perpendicular to the direction of motion. We don't need to necessarily solve the y equation, although it's useful in cases with friction. So again, I will probably go ahead and do so just to show how it sets up. But gravity would break up into components. And the way that we break this up into components is as follows. We have a ramp angle here, theta. Because that is theta, if I look at this triangle formed by extending the vertical direction of gravity, this is a right triangle, therefore this angle is 90 minus theta. But because this y-axis is perpendicular to this ramp, that means this whole angle is 90. So, and because these angles are complementary, they have to add up to 90. So 90 minus 90 minus theta gives me theta. So it's always, let me redraw this to make this clear. It's always going to be the case that for these ramp problems, if this is your force of gravity and this is theta, the angle that gravity makes relative to the y-axis will also be theta. Now this is relative to the y-axis, which means that sine and cosine for x and y are a little bit different. Usually we define our angle relative to the x-axis. My neighbor is starting his motorcycle. Because it's measured relative to the y-axis, that means the y component for gravity is equal to mg cosine theta, because that's adjacent to the angle. That's the adjacent side of that angle. Whereas the x component will be mg sine theta. So make sure you're clear on that. Make sure you do not draw your gravity like this, right? The actual magnitude has to be the hypotenuse. We draw our triangle this way. And if you draw it this way, this angle will always match this angle. So going back to solving for, let's say, the y direction, sum of the forces in the y direction equals mass times acceleration in the y direction. The block is neither moving up, off the ramp, nor burrowing into it, so the acceleration is 0. And so in the y direction, we have normal force minus the force of gravity in the y direction. As I've explained here, force of gravity in the y direction is mg cosine theta. So the normal force on a ramp problem where the block is sliding along the ramp will be mg cosine theta, assuming no other forces in the y direction. This will change if you have, let's say, an applied force going this way or this way, where there's a y component. But in the absence of that, this will be a result that you see a lot on these ramp problems. But I want to emphasize, when you're solving for normal force, set your sum of forces in the y direction equal to mass times acceleration in the y direction, and solve explicitly for your normal force. Do not assume this is going to be true for every single ramp problem. This is true for every ramp problem for which there are no other y component forces other than normal force and gravity. So what about in the x direction? We only have gravity. Sum of the forces in the x direction equals mass times acceleration in the x direction. And so we have gravity, which is acting in the positive x direction, so that would be positive based off of our coordinate system. So we have fgx equals max. We replace that with mg sine theta. The m's cancel, leaving us with the result that the acceleration is g sine theta. What if we had friction? If we had friction, friction opposes the direction of motion. Let's assume that the block is sliding down the ramp. If the block were sliding up the ramp, friction would have to go this way. So it is very important to emphasize we need to know the direction of velocity in order to apply friction. So if we do this again, I'm going to explicitly solve for normal force again. And because we have friction, we actually do need this. If we set up our F equals ma equation in the x direction, now we have two forces with components in the x direction. We have gravity, which again, we use that theta to get our components. Now friction is acting in the negative x direction, so that's why there's a minus sign in front of the magnitude of friction. Friction itself is the coefficient times the normal force. And we can actually go ahead and replace our I'll go ahead and show it in steps. Normal force is mg cosine theta. Notice there's an m everywhere, so we can cancel that. And so our acceleration is going to be g sine theta minus the coefficient g cosine theta. You could factor out a g if you needed to, but it's not necessary. One slight note on these ramp problems. When we start with circular motion, we will be dealing with banked curve problems, which superficially look like a ramp, but the net acceleration will actually be toward the center of the circle. In that case, you will not use a rotated coordinate system, and your value for normal force that you derive will be different. Not something to worry about now, but it is coming. Just know that for blocks sliding up and down a ramp, we are going to use a rotated coordinate system. One last thing I'm going to cover will be pulley problems. And with these pulley problems, or these connected object problems, you will have a choice whether to treat each individual object as its system and do a free body diagram for each, or treat the combined motion of the objects or derive the combined motion of the objects by treating the whole thing as a system. Let's start with as simple a pulley problem as we can make. Or maybe not the simplest, but fairly simple. I have a block of mass MA. I have a hanging block of mass MB. There is a friction coefficient here, let's say with a kinetic friction coefficient mu k. So it will be sliding, so I don't worry about a static friction component. And this will be an ideal pulley. What will happen is basically these objects will be moving like so. This object will be falling, and because this string is taut, this object will be moving to the right. And because the string is taut, for every meter this moves, this will move 1 meter. For every meter per second squared this accelerate, this will also accelerate the same amount. So for this reason, we're going to choose a slightly weird coordinate system. We're going to choose a standard coordinate system of x, y here. X is in the direction of motion. And we need to make sure that this positive x traces the direction of this rope, which means this will be positive x in order for it to be consistent. If you think about how this moves this way, same amount this moves this way, hopefully that makes sense. But just know that for connected objects, you want one axis of motion, or one axis of your coordinate system, to follow the direction of the rope. And so, how are we going to solve this? We can draw a free body diagram for each of these individually and solve for the acceleration, which we'll do first. And then I will show you how to do it by treating the whole thing as a system. So let's start with MA. We have a normal force, a force of gravity. Those are going to be equal because there's no acceleration in that direction. We have a tension force. Well, I'll just call it T. And we have a kinetic friction force, which are not equal because presumably this is larger than this, causing this to accelerate. We have MB, and I will actually copy my coordinate system here just to make sure I know which directions are positive. We have MB. It is experiencing a force of gravity, and let me call that force of gravity B and force of gravity A to avoid confusion. And it is experiencing a tension force as well. I don't have to label these separately because, again, for an ideal pulley, if the pulley is ideal, the tension should be the same here and here, as well as here and here. And this is in the positive x direction. And presumably this one should be a little bit larger than tension because the net acceleration will be that way. All right, those are my free body diagrams. In order to solve for the acceleration, first of all, the acceleration of this object will be the same as this object. So I'll say acceleration A equals acceleration B, which I'll just call A, because the string is taut. And now I can do F equals ma for each of these objects individually. So I'll start with the y direction because I do have friction. And I'm being careful with my subscripts because that's mass A. No acceleration in the y direction because that block is not burrowing into the table, nor is it flying up. So I end up with normal force is equal in magnitude to the weight of the object. Now let me switch to the x direction. And again, because these accelerations are the same, I'll dispense with using AA, AB, and just call it A. Okay, so I have one equation right now, which I will box and label 1, Notice that I have two unknowns. I have the acceleration of this object and the tension on this object. With two unknowns, we're going to need two equations, and we're going to get our second equation from the second free body diagram. So if I switch now to mass B, sum of the forces in the x direction equals mass B times acceleration in the x direction, which I'm just going to call A. Down is positive, so the force of gravity on B minus tension equals MBA. Force of gravity on B is just mass of B times G. And now I have my second equation. For these pulley problems, or for these problems involving connected objects, you'll generally be able to add the equations to eliminate tension. The reason is tension is acting in the positive direction on one side, negative direction on the other side. So if I can add these equations, let me write equation 2 under this one to illustrate it. So I'm going to change the order a little bit, put the negative t here, plus mbg equals mba. And if I add equation 1 and 2 here, the tensions will cancel out. I'm left with positive mbg minus mu k mag on the left side. On the right side, I'm left with maa plus mba, which I will factor out the acceleration. And then I will probably factor out the g on this side. And then divide over, and I get my acceleration for both objects. What you'll be asked to do often is to consider what you'll be asked to consider certain things about this, like limiting cases. So for instance, if the coefficient is 0, there's no friction, this will be mbg over ma plus mb acceleration. In other words, the force of gravity of this thing is equal to the total mass times the acceleration. What if mass of b went to 0? Well, the acceleration should go to 0, and you end up with, does that work out? Okay, I'm sorry, let's do, what if the mass of a goes to 0? Well, that term is 0, which means you have mbg over mb, so acceleration will be g. This will be in free fall. Okay, I know this video is a bit long. Last thing I want to do is show you, well, did we have to solve for these individually? What if we treat this whole thing as a system? So I'm going to basically represent this as a whole system. The way I'm going to do this is I'm going to tilt this up. So I'm going to redraw this as MA, MB, draw a dashed box around it to indicate that my system is the entire object, and I'm going to draw only forces acting from outside the system onto parts of the system. I still have a coefficient of friction here, or a friction force here. I still have a normal force here. I still have a force of gravity on this one here. I still have a force of gravity on MB now acting this way because, again, I've sort of rotated this part up to represent this as just motion purely in the x direction. I do not have tension anymore. Tension is an internal force. So the fact that tension is acting here and tension is acting here, they cancel out because now my entire system includes both of these. So action-reaction says these are equal and opposite and acting on different pieces. However, because I'm grouping the pieces that they're acting on, all action-reaction pairs that are within the system do not show up. So this makes it a lot easier to solve for our net acceleration. So the y direction stuff will be the same, except it'll be F equals total mass times acceleration. We still have normal force minus MAG equals 0. Normal force will be MAG as before. The x direction equation, sum of the forces in the x direction, will be the total mass times acceleration. So that'll be MBG minus the friction force equals the total mass times acceleration. I know I'm skipping a couple steps relative to before, but even if I were not to skip those steps, I would arrive at my acceleration much more efficiently. So at the price of a little bit of conceptual work to reconceptualize this system, or these two individual objects, as a single system and rotate this piece to make it a little more consistent as far as right-left motion, I'm able to set up a free body diagram for the system as a whole and set up my F equals ma equations and get my acceleration more quickly. Now note, you will not be able to solve for tension using this. So if you solved for acceleration here and then you wanted to solve for tension, you need to find a new system, probably either individual block. This is probably a little easier. When you do so, tension re-emerges, and you could do F equals ma on this one and solve for tension. Basically, you have, in order to solve for a force, or in order for a force to show up in your equation, it has to cut through the box that you define as your system. So if it's an internal force, you can't do it. The way you do that is to redraw your system such that whatever internal force you're looking for is now an external force on your new defined system. Okay, hope this helps. See you next time.